All right, thank you. I'm ready to go. So, yeah, thanks for that introduction, and thanks for the invitation, Mona. You know, I've been chatting with Mona a bit about not just this kind of lithium trilogy, but broader. I think she refers to it as a lithium universe around these different issues, and was asked to come and give kind of an overview of where we are, and then in terms of how much lithium we're making. I can give some comments too, as far as like things that my research group is working on, although I don't have a lot of slides dedicated to that. And then also a couple comments related to battery recycling as well, which I think is something that's going to be really important moving into the future. And so just to give you an idea of kind of why and how important this has become. So I pulled some data just from US Geological Survey, not necessarily comprehensive of everything that's out there, but as far as being like publicly available data sources, it can be helpful, and especially being able to pull from the same one over a long time period. But this is representative, just showing like global lithium production. And I chose the year in the mid 90s because when you talk about lithium ion batteries, you're really talking about a technology that, Sony had the first commercial cells in the early 90s. And before that, there were some rechargeable lithium systems, but they were not that prolific. And there were a lot of single-use lithium systems. In fact, there are even still small form factor batteries today that are based on lithium metal anodes. But when you talk about the rechargeable ones, it was really the early 90s. So in terms of the amount of lithium that's being mined, you see that there was at least, on the order of a few thousand metric ton scale in the mid 90s, but this has grown dramatically. I mean, it started to tick up quite a bit as we got over I don't know, this 10 or 15 years here, but then it's really jumped up a lot. And the earlier sort of rise was really driven by portable electronics. So, moving to even some of the earliest iterations were really things like Walkman for your headphones. Japan was one of the earliest adopters, in part because of environmental concerns, with as many single-use batteries as are being thrown away once people started to use these portable devices. But when you look at cell phones and laptop computers and things of that nature, that really drove that initial rise that you see there. And then more recently, you can see there's been a much sharper spike. And I'll get into a little bit more on some of that data too, but that's really part of what you're talking about here as far as this energy transition and just energy transition, because it has to do with the scale of the batteries that are being made. Another comment that I'll add here too is that at least to me, I mean, there's a lot of, I don't know, critical elements and compounds and involved in lithium ion batteries. Cobalt gets a lot of attention. Also some fluorine species that are in the electrolyte, nickel. But when you talk about lithium ion, it's not a single chemistry. Lead acid is largely the same chemistry across a lot of different cells. Lithium ion is many different possible combinations of cathodes and anodes, but all of them still do rely on lithium because that's what moves. And when electrons move, the lithium moves too. And so even as I think of like near term, longer term, even pretty further out term, because a lot of times the next generation of batteries beyond lithium ion involve like lithium metal as the anode, I think lithium is going to be a very significant player here, especially as we move towards battery powered electric vehicles and then battery storage at the grid scale to level intermittency. Another way that you can really see that it's been driven by these larger scale applications and the fact that we're starting to use, Teslas and other EVs, and then also even grid scale storage and leveling, is the amount of that lithium that's being produced that's going towards lithium batteries. So even though we were already in this range here, so, I started really working on lithium ion batteries around here, and 2009 range. And even though we were making billions of units per year of portable electronic batteries at that time, lithium was not the main sort of end use of it was not really for lithium ion batteries. In fact, Lithium is used in a lot of other applications. It shows up significantly in glass manufacturing, also like lithium greases. There are also some like specialty products, like in pharmaceutical, even as a reagent and a lot of other chemical processes. Um, but even as not so long ago as when I finished my PhD, it was still only about 20% or so of the lithium was going towards lithium-ion batteries. And then you can see that starting in about 2012 onward to now, that percentage is gradually increasing. We're over 80% of the lithium that's being produced now is going towards batteries. And as I'll kind of reiterate again, that really has to do with these larger scale cells that are being produced. So when you're going to like electric vehicles and grid storage, I'd say right now, at least, it's really more electric vehicles that is the big driver there. Just another short kind of way to summarize that. The orange is lithium that's going to everything that's not batteries. The black is what's going to batteries. And so that's really where it's showing up the most. So, just to kind of, I think in some ways this is obvious, but to really give a feel for that scale. So this is a figure that's taken from a recent paper that was in Nature related to, actually, this is more focused on lithium ion recycling. But, when you deconstruct an electric vehicle battery, there's a few different configurations in terms of that smallest like core unit. If you look at, and this is, if anybody has questions and really wants to get into details of the design, there's a little bit of even an older design in terms of this form factor, but some of the most common batteries are in this like cylindrical, so they look a little bit like the AA's that you might see in the store. You get a whole bunch of these that you combine into a pack, and then your packs get combined into a module. For this battery that's shown on the far left column here, each of those little cylindrical cells is about 3 to 3.5 amp hours. And to give you an idea of like how much capacity that is, that's on the order of what your cell phone probably has. My cell phone might have a little bit more than that, but there are a number of cell phones that are kind of in that range. And so if you kind of multiply this out in terms of like all these little cells and then into these 16 modules per pack and et cetera, going into the big pack level, you're talking about like over 7,000 cells. And so, basically one EV is on the order of many thousand, cell phone size batteries. And so you start to see, if you're thinking about making, there are some vehicles that are sold just in the US on the order of 1 million per year. And so now you're talking about something that's on the scale of like, 1 billion sort of like cell phone scale units that might be just from, one EV brand coming there. And so that's really what's bringing that into play. There are a few different things. I don't know. I don't think for this audience to go into too many details, but there are lots of other configurations. So like you can even see in this picture, you can have ones that are more like prismatic or pouch style, and those can like pack differently. They can be of different sizes. There's all kinds of different configurations. But in general, in terms of the total amount of lithium that's going to be in there, it's going to be a lot. I'll also mention here that I kind of put on the right, but when you think about like a grid or stationary system, these can easily be sort of at the pack units. Well, it's not really the pack unit because they're really more like towers that are stacked in, but it can easily be 10 times the scale of what you might see on an individual EV battery, and then even these battery installations for backup power or leveling. Well, actually, most of them are power quality. They can, and then there can be multiple in like an individual installation. So you're talking about a lot of equivalent cell phone batteries at one location there. The other thing is a back of an envelope calculation that I think is really important to see is that if you take about actually a little bit less than half of just the light duty fleet in the US, so we're not talking about like electric semi trucks or medium duty vehicles. These are all light duty fleet. You take about half of it, you assume about 50 kilowatt hours. That's actually smaller than some of the extended range, like, Rivians or Teslas that you'll see, but maybe we'll assume that it's about 50 kilowatt hours. If you use like current technology in terms of how much lithium needs to get in there, you're probably talking about something on the order of 800,000 metric tons of lithium just for the US, just for half of the light duty fleet. And so if you go back and look at that number, here's 100,000 right here. You're going to need 8 of those just to get to half of the US fleet being replaced. And so I think that kind of paints a big picture of like how much more capacity is really going to need to be ramped up to try to meet some of these goals that are being set around the world in terms of translating to EVs. I think it also is important in thinking about if you have that many vehicles on the road with that much lithium, how much of a sort of a mineral resource you have just in your vehicle fleet then at that point, in terms of the value of that lithium that you have there. So when you have everybody trying to make a lot of batteries at the same time, even though the production of lithium is ramping up, this has also led to a lot of price volatility. And I mean, price volatility is kind of complicated, especially if you look in these last couple of years in terms of just supply chain and global trade in general with the pandemic. But price is also complicated because it also depends on how long the contracts are, especially with like the bigger manufacturers that get into. But this is at least publicly USGS data related to US based prices, and this is the price for equivalent per ton, lithium carbonate equivalent per ton for battery grade. It's important to note that cost always depends on purity, and the purity for like making lithium ion batteries, the lithium sources that you use is relatively higher, a lot higher in many cases than what you might use for something like glass manufacturing. But this is the price point for at the sort of purity level that you would expect related to battery grade. And going back again, when I got started in this field, maybe $5,000, $6,000 per ton was pretty typical. You might see little fluctuation. You might see some fluctuations here and there, but that was about the price point. These are annual average values. Actually, when these sort of spikes were happening a year or two ago, I think I saw some different news articles that talked about it hitting like $60,000 per ton. And so that goes from being something that at an EV scale is, I mean, you always try to keep your price down as much as possible. But that goes from something that is not as big of a price input to being actually a pretty significant price input if you're getting to like a 10x increase in that price. And so the thing to look at here is that obviously also depending on the price, that's going to depend on what other kinds of alternative production resources might be explored that might start to become economically viable. But if the price is already going up like this and there's going to be that much proliferation, I wouldn't really expect it to be necessarily less volatile. But that is a pretty major consideration. And if it gets too expensive, I think it starts to be a bit of a hindrance, especially if you're talking about stationary applications, which really the price point of those batteries needs to come down for a lot of the applications related to intermittent leveling. I think it's also helpful, and I know that some of the context here has talked about like the places where lithium is being produced. So here's a pie chart on the left showing the location. Right now, if you look at this kind of orange cutout, Australia is the largest producer of lithium products. But of course, and it was even mentioned in that introduction, like the Atacama Desert, Lithium Triangle. So Argentina and Chile are also pretty significant players. So here's Argentina, here's Chile, and then China has a pretty significant wedge here as well. And so there is a bit of, I guess, breadth in terms of where it's being produced, but it's largely Australia, South America, and China are the places where it's showing up. And even in South America, though it's a big continent, I mean, it's kind of a pretty localized region where most of it comes from. There is a little bit produced in the there's some produced in the United States. A lot of those numbers are not as as easy to find, but I mean, there are some facilities, for example, out in Nevada. If you think about where it also might be coming from in the future, so this is a different pie chart on the right that's identified lithium resources. Lithium resources is a little bit complicated because it sort of depends on how viable and accessible some of those resources actually are. But a couple of things that I'll maybe point out is that one of the biggest wedges on here is Bolivia, for example, which is in terms of location in South America. I mean, there are really large reserves. Also, those desert Atacama mining locations. There's a lot of reserves that are available in Bolivia, but a lot of it has to do with what's the different investment of industry and relationship between industry and nations that has led to, I would say, at least those resources being not as well developed as other places there. The United States also has some significant resources, and in fact, historically, was a producer as far as like spodumene, and is doing some now. And I think there's also some potential untapped resources. My own research group looks at trying to recover from geothermal brines, but and just to give a feel for where lithium comes from. So I have seawater here. Seawater is not actually used as a commercial resource, but there is a lot of seawater and there's a lot of lithium in it. It's really hard to extract something that's at that really low concentration. With the ore, so you're digging rock out of the ground, but there's a lot of chemical and energy inputs that goes into processing ores. You have to like calcine them. You have to release the lithium out of that rock somehow. You treat it with acid, and there's a lot of chemical and energy intensity that goes into producing it that way. But you can make a relatively high concentration of lithium, and concentration is important from like a processing standpoint and keeping it economic. Brine. So this is the way that largely it's done in South America, in South American countries. The thing about brine is it's kind of it's a longer time scale process. But when you're concentrating that lithium to make it easier in terms of like the equipment intensity, you're taking advantage of putting it into these giant pools and allowing solar evaporation in the desert to concentrate that lithium that you need. So it's not like you have to necessarily have as large of energy inputs, like burning natural gas or something to drive off a lot of the water to concentrate it. You can rely on sort of more natural processes. But that does mean that there's a lot of water that's going up into the air. And so there is some concern over the water intensity and water use there. So I wanted to spend the last little bit here talking about recycling, and something to appreciate here is, first off, in the battery world, I would say that lead acid batteries are a pretty good success story in terms of recycling. The recycling rates are relatively high. There's a robust, infrastructure and policy and market for those products. But in large part, there aren't as many components as a lithium ion system, and they're in very high concentration, and they're all very different. Metal, lead, and like the container polycarbonate, or whatever it is that they're using to hold it in, and then the sulfuric acid electrolyte, they're quite different in terms of coming up with relatively not too complex separation processes, and they're in very high concentration in many cases within the cells. For lithium ion, you're talking about something that is, if you take apart a cell, it's quite tightly wound up, and there are many layers, and those layers all have multiple components, and those components are quite different. And you also have to be able to access them. So if I go back here, you have to think about taking apart the vehicle and then breaking down the pack and then accessing the modules and then pulling out the cells. And then after you pull out the cells, you have to be able to extract out these individual components. I mean, this is also what the roll looks like, sometimes called the jelly roll. And then you have to go through whatever additional processing you need to do to get it to the easiest state to recycle these materials. Hopefully recover as many as you can, but you're only going to be recovering what's going to be an economically competitive new product that can be used as a raw material to a new process. And so there are some real challenges in terms of, accessing the material in the lithium ion cells. The other thing is that, as I mentioned before, there are lots of different types of lithium ion batteries, and it's very difficult if you think about, like, if it's a manufacturing process and it's reject cells, then it's relatively easier to, like, you would know what was going in there. But if you have like a huge collection of cells from lots of different, vehicles or grid batteries or whatever they might be, they could have really different compositions. I mean, yeah, they probably, they pretty much all will have lithium, assuming that they're in the right pile. But the other components and constituents can be quite different. And so thinking about like what that recycling process looks like to have to handle a wide variety of compositions, can be really challenging. There are, and this is a bit of a messy slide, but there are basically, I would say, three routes that are looked at with regards to recycling, and there's all kinds of different flavors and iterations and commercial processes either being developed or in practice. The three main ones are really pyrometallurgical, hydrometallurgical, and direct. So with pyrometallurgical, and what you might be able to see here is, yeah, there's all these other independent steps, but if I take batteries and I go over here and I hit this, then I skip a lot of those to go to pyrometallurgical. And so that has to do with you taking it to really high temperature, you're burning off a lot of components, and you really end up with just sort of like slag and alloy. And a lot of times you're really only recovering kind of the highest value alloy component like cobalt. So, you're taking a whole lot of battery and you're really condensing it down to a kind of the relatively small thing that's the most valuable is really the focus of that kind of a process. So the simplicity helps a lot, but it's something where if you want to really try to recover as many materials as possible, it's a tough way to do it. Hydrometallurgical is also, I would say, growing. That's where you end up with a lot more of these in-between steps, doing this physical separation, extracting out a lot of more of the individual components. You're going to be doing a lot of chemical and energy inputs in order to start to separate out the different pieces. I mean, you can see some of these different boxes as far as like, lithium recovery, cathode, slag, et cetera. So there's a lot more, I would say, steps involved in hydrometallurgical. You can recover more of the components, but you have to be able to recover them at the purity and cost point where you can be competitive with other, raw materials that aren't being produced from these recycling processes. And then the last one, which I'm not really aware of anybody truly taking in like recovered sort of spent cells and doing this, but is direct. And the idea with direct is really that you take the materials that have the highest value, sort of the solid materials that actually store and deliver the energy, and you have some sort of a method for kind of like refreshing them, and then putting them into new cells. And I think there's a lot that makes sense there in terms of, thinking about, well, that is the highest value component and we don't have to take it down to the original constituent materials, but there is a challenge there in that, how well do you know exactly what was in all those cells that you're recovering? And can you design a process that is flexible to a lot of different types of input materials that might have to go in there? And then the other thing is a big one is if these batteries are going to be in service for a long time, hopefully, right? Like if you think of a grid battery, 10, 20 years, are you really even going to be using the same material and technology 10 or 20 years later? So it's something that I think makes a lot of sense, especially with like scrap recovery. But I think there's a lot of things to sort out with the thinking like longer term using a direct recycling method. And that's all I had today.